We talked about inverse relations yesterday and defined what an inverse function is. We're just going to look at inverse functions in a little bit more detail. The symbol we use for inverse function is this -1 there. Now, it's important not to get it confused with the power of -1. It does not mean reciprocal. Okay, so that's the symbol for inverse function. Now, the composite function of a function and its inverse function is always x. So composite functions, remember that's when you substitute one function into another one. So basically what we're saying is, if you substitute the inverse into the function, you should get x. If you substitute the function into the inverse, you should get x, because that's what the inverse does. It returns it back to where it started from. So as an example, let's do this one. X minus 2 and x plus 2 is the original function. So I'll work out the inverse by swapping the x and the y's around. Now I want to make y the subject, so I know what we're going to substitute into. And eventually, after a little bit of algebra, we get that the inverse function would be 2x plus 2 on 1 minus x. So if I was to substitute the function into the inverse, so the original function, x minus 2 and x plus 2, substitute that into the inverse function. Well, the first thing I think I'll do there is multiply everything by x plus 2. Get rid of the fraction on a fraction. And then that tidies up quite nicely. And yes, we get x. But just to prove it works the other way around as well, let's now substitute the inverse function, 2x plus 2 and 1 minus x, into the actual function itself. Again, we notice the denominator is the same, so I'll multiply everything by 1 minus x. And yeah, that turns out to be x as well. And that's what we are expecting to happen, because the inverse, remember, sends it back to where it started from. Okay, domain and range. Because all that's happening is that the x and the y's are swapping, then if AB is a point on the original function, then BA should be a point on the inverse function. The x and the y's have swapped around. The domain of the original function would become the range of the inverse function. And the range of the original function becomes the domain of the inverse function. As I say, everything just swaps over. So let's have a look at y equals e to the power of x. So it's an exponential, but the base is the wonderful irrational number e, which is approximately 2.7172 something, I think. Anyway, it doesn't matter. We don't need to know that at the moment anyway. It's our basic exponential curve. That's all that we need to know. All right. Well, the domain of that curve is all real x. And we can see that its range is y is greater than 0. Now the inverse, so I swap the x and the y's around, because it does have an inverse function, satisfies horizontal line test, satisfies vertical line test, is x equals e to the power of y, but if I was to make y the subject, we get a log curve. Its domain is the range of the original one. So its domain will be x is greater than 0, and its range will be the domain of the original one, so its domain will be all real y. The other thing we saw yesterday is we should see them being reflections of each other in the line y equals x. So I've just drawn in a very faint y equals x there, and that would be our log curve. So you can see they reflect. They actually have no point of intersection, those two curves. They have no point in common. If you think about it, not many functions are going to have an inverse. The only functions that will have an inverse, well, the term we used there was 1 to 1, but if you think about it, the curve has to be continually increasing or continually decreasing. Because as soon as it turns, it's going to fail that horizontal line test. Not many functions do that. I mean, have a look over there. Parabola, no. Hyperbola does. It's continually decreasing, you will notice. Right? So if you look at the hyperbola, yes, it's in two sections, but the curve is continually going down. Cubic, that one's okay. Circle, well, circle, of course, is not a function, so you can't have an inverse function if it's not a function originally. So what we need to do then is to just get a piece of the curve. So It's up to us which piece we choose, but we try and include 0 if we can. X equals 0 is always a good one to try and include. And we tend to go with positives rather than negatives, but it doesn't really matter. But essentially, we're grabbing a piece of the graph which is always increasing or decreasing. So let's have a look at our parabola. There it is, and we know it fails the horizontal line test, not going to work. Well, the domain of the actual function is all real x, and the range is y is greater than or equal to 0. I can't use that domain though, because it's got no inverse over that domain. So I want to pick a piece of this parabola which is either continually increasing or decreasing. So I suppose we've either got the left-hand side, which is always going down, or the right-hand side, which is always going up. I would tend to go with the positives, so I'm going to choose x is greater than or equal to 0. If I just use that piece of the graph, then I've got a function that's continually increasing. And if I do that, the range stays the same. It hasn't changed. It's still y is greater than or equal to 0. Turns out, when we substitute in, we still do it the same way. Swap the x and the y's around. But whereas before we said y was equal to plus or minus the square root of x, we now know, well, I've restricted it so the range is going to be positive. So therefore, it must be y equals the positive square root of x that I've chosen. If I had selected the left-hand side, then it would be y equals the negative square root of x that I would have chosen. Domain is now the x is greater than or equal to 0, and now the range actually matches the domain for this one. But if we were to draw it, there's our half a parabola on its side there. It says y equals the square root of x. What it means is, this is another way we could, I'm not suggesting that you do necessarily, but it's another way that you could find the range of a function. Because a range of a function will be the domain of its inverse. And sometimes people find domains easier to find than range. So you could work out the inverse and then find the domain of that. As I say, I'm not suggesting that you would do it this way, but it does give us an alternative. So okay, well, let's play around with the parabola. We've got y equals x squared. For some insane reason, we can't work out the domain. I'm going to change it to capital X and capital Y so I don't get the two confused. So I swap the x and y's around. My inverse will be capital X equals capital Y squared, which means y equals the square root of x. Now the domain of this new function, capital Y equals the square root of x, is capital X is greater than or equal to 0. So therefore the range of the original function must have been y is greater than or equal to 0. That's not probably not the best way to find the range for that function, but it illustrates what you could do. So x squared plus 3, again I'll swap the x and the y's around, make y the subject. Now the domain of that I can find, that's going to be capital X is greater than or equal to 3, so therefore the range of the original function must have been y is greater than or equal to 3. Absolute value of x plus 2 minus 5. Again, let's swap the x and the y's around. This one's a little bit more interesting to make y the subject. So x plus 5 is the absolute value of y plus 2, which means I now know that x plus 5 must be greater than or equal to 0. Because you can't have an absolute value ending up in a negative number. So the domain of my new function is x is greater than or equal to negative 5. So the range of the original function, y is greater than or equal to negative 5. So you can see that it does work. It does give us an alternative. Y is the square root of 4 minus x squared. Again, it's something I would hope we would look at and be able to go, oh, that's what the picture looks like, so bang, there's my domain and range. If we swap the x and the y's around, play around with it, make y the subject, and I get the domain of the new function is minus x is in between minus 2 and 2. But hang on a sec, and this is where it doesn't necessarily work. Because remember, the original function was that y is greater than or equal to 0. Because you can't find this. When I find a positive square root, I can't get a negative answer. So it doesn't necessarily work 100% of the time, because this would suggest that the range of the old function was in between minus 2 and 2. But I can't get answers of minus 2 for that. This one is a function, Are we in agreement? Oh, good. So we swap the x and the y's around. I end up with that. Capital Y is 7 minus 4 capital X over capital X minus 1. It has a domain of all real x except x equals 1. So therefore, the range of the original function, all real y except y equals 1. I think a little polynomial division is going to be quicker personally, but all I'm pointing out here is it gives us an alternative way of doing it. So, okay, 5 G's on inverse function.